All right, so significance tests for the difference between two proportions is not much different. It's just a hypothesis test. The conditions are the same. Uh, both samples are random. Both samples pass the 10% condition. All four large counts check out, and independent samples exactly the same. Our null hypothesis is going to be that the two proportions are equal, or that the difference in the proportions is 0. By the way, we can do differences other than 0, but in AP Stat, we don't. That's kind of a BAPS beyond AP Stat topic. So we'll just always have a difference of 0. Against the alternate that the difference is greater than 0, or the difference is less than 0, or the difference is not equal to 0. We got one-sided alternates here, two-sided alternate here. When we ran a one-sample test, we used the hypothesized value of the proportion for the standard deviation of the sampling distribution. Because the assumed null hypothesis is that the two proportions are the same, then our best point estimate for the overall population proportion is to pool both these samples together into one large sample and use that combined proportion as our best guess estimate for both of these. It doesn't really make sense to have a null hypothesis that they're the same and then to put in a 40% for P1 and a 50% for P2. That doesn't make sense. If we're assuming that these are the same, then why would we use two different values, right? So what we do is we put these together. It's basically kind of like averaging them, right? Put these together and say, well, the average is 45. Well, the average is going to be 45 if the sample sizes are the same. If they're not the same, then you're going to do a weighted average. This is basically just a weighted average. So our P hat sub C, or our combined sample proportion, is put the sum of the successes from both samples divided by the sum of the sample sizes. So your successes divided by the total. Pool it together into a single sample. Since this is our best guess for both population proportions, we should use this value in the standard error formula. So the standard error for P hat 1, P hat 2, when we're doing significance tests, more specifically when we're doing significance tests where we're hypothesizing that they're the same, is to put that same value in for both the numerator spots in both of those. You still divide by n1 and n2, but yeah, so that's how it is. That's how it's done with hypothesis tests. So the z test statistic, remember, your test statistic is always like a z-score, x minus the mean over the standard deviation. In this case, for hypothesis tests, it's your estimate minus the hypothesized parameter, if you want to call it that, divided by the standard deviation of the sampling distribution, the standard deviation of your estimate, okay? So our best guess for the difference is going to be the difference in your two sample proportions. Hypothesized value is 0, and then this is our standard error estimate for the sampling distribution. Note, we are now at the point where the formula is becoming kind of too difficult to remember, and the details, the hats, the sub C's, there's just a lot of different things that you can mess up. You should be able to do it, but on the AP test, you either have to give the proper name or a proper formula. Because the name is probably easier to come up with than the formula, I'm going to recommend let's just go with the name. All right, example. You are comparing the proportion of successes from two populations using a two-sample z-test for P1 minus P2. The hypotheses and samples are from each population are, so here's our null and alternate. We're doing a two-sided alternate. And then these are our sample proportions. So for the first one, there's 16 successes out of 25. For the second, there's 57 successes out of 72. Find the pooled proportion by hand. So what we do is we simply pool these two samples together. We take the total number of successes divided by the total sample size. What's going to happen here is we're kind of averaging these out. This is 64%, this is 80%. Now if I were to go halfway, it'd be kind of whatever, I don't know, whatever that would be. 70, I don't know, 1. But because the sample size is bigger, this one's going to carry more weight. So it's going to be closer to this one. So it's probably going to be like 77 or something like that. So let's put that into our calculator. So hit Control Enter. I put it in my calculator already. 75%. 753. Okay. And it's a little closer to this one than it is to that one. Okay. Explain why PC is used to calculate the statistic instead of the sample proportions. Because we assume the null is true. And that P1 equals P2. So we pool to get the best estimate for P1 equals P2. Okay. Calculate the test statistic. Test statistic is a z-test statistic. It is your estimate minus your hypothesized parameter divided by the standard deviation or standard error. In this case, we're going to use that and I didn't mention this, but the thing is when we have these two proportions, we don't have an estimate for the true proportions at all. We just know they're the same, so we don't have an actual value. So I can't put in the standard deviation. Usually I would put in the standard deviation when doing a hypothesis test, but so we got to put in the standard error of our estimate. So that's going to be, what is this here? So we're doing P1 minus P2, so P1 would be 0.64, minus 0.792, minus the hypothesized difference is 0. I should just make this smaller, 0. All over the square root, put in your P hat C, then the complement, that's 0.247 over your sample size for 1, plus put in the exact same estimators for your second sample. That's it. Put that in the calculator. All right, so I typed this in my calculator. I did use the last answer to avoid some rounding here, but I might have some rounding errors on these, so I don't know how good this is going to be, but whatever, it's going to be okay. Control Enter. Negative 1.517. So my Z test statistic is negative 1.517. And then calculate P hat sub C and the test statistic with the calculator. Okay, so when we run our test with the calculator, it will do the pooled proportion for us. It'll do this for us. It'll do everything for us. Now you should still know how to kind of do it in case I give you a different question or I test to see if you know how to do it. But when we run these tests, we just type it in the calculator. Stat tests. This is a 2 proportion z-test. Successes, 16 out of 25. What was it, 52? 57 out of 72. 57 out of 72. Alternate was, what was it, two-sided? Shouldn't really matter unless you're the one-tailed or two-tailed are the direction that only impacts the p-value, but whatever. So test statistic is negative 1.514. I think I was off just a little bit. I said 517. That was because these were probably estimates here. Like these probably weren't exactly 64 and 792. So that's where my error probably came in. And if you look through here, here's the p-value. Here's the first proportion. See, there you can see that second proportion wasn't 792, 791,667. This right here is your pooled proportion. The calculator just calls it p hat, but we call it p hat the combined. So it does calculate it, it does use it, but it just does it in the background. Okay? All right. Hearing loss. So we got a couple of examples here. Let's just go through these here. You should already be filled out in your notes. You believe that the introduction of MP3 players and iPods have caused hearing loss in teens since their introduction in 2002. In a study of 3,000 randomly selected teenagers in 93, 15% showed hearing loss. 1,800 teenagers in 2005, 19.5% showed some hearing loss. Do these data provide convincing evidence that the proportion of teens with hearing loss in 2005 is significantly higher, highlight that, than the proportion of teens in 93 that had hearing loss? Perform at a significance level of 0.01. So it looks like we went from 15% to 19.5. That is definitely an increase, but it's an increase in our two samples. Do these data provide evidence that the population increase, or could this difference be attributed to chance variation? P, parameter, the true population proportion of all teens in 93 with hearing loss, we'll call that P sub 93. P sub 05, ditto 2005. Null hypothesis is that the difference is 0. You can do the difference any way you want. You could be P93 minus 05, that's fine. I like to always put the bigger proportion first. So I did 05 minus 93. And then if I want to know if this is higher, if this is higher than this, then this minus this would be a positive difference. So my alternate is greater than. Now, if you chose to go the other way, that is fine, but your alternate should be less than. And your test statistic will have the opposite sign, but your p-value will be exactly the same. So it really doesn't matter how you set it up, okay? Just be consistent and do it right. Check the conditions. Both samples were randomly selected. 10% condition, n equals 3,000 is less than 10% of all teens in 93. 1,800 is less than 10% of all teens in 2005. Check them for both. Large counts, we're checking 4 different things. You don't have to write this, but you do have to have that either that number down or the product to show the number, and just say and you do have to compare it to 10. Okay. This is not required anymore, as I mentioned in class. That's something that we can just screw up. So I don't like this of interest. I didn't even say which one I was talking about. Therefore, the sampling distribution of p hat 05 minus p hat 93. That's the sampling distribution that is approximately normal. Don't put it down. It can only cost you points. And the samples are independent. Don't forget this. It's common for kids to forget that. So the conditions all check out. Name the test. This is a 2-sample z-test for the difference in proportions. Now you just type this in your calculator and you're good to go. I don't know if you want me to type it in my calculator to illustrate it. I guess I will. Got a couple minutes here. So I put in 05, 93. So I got to put in 05 first. 05 was 19.5% of 1,800. So first of all, is 0.195 times 1,800, is that an integer? I'm sorry, that should have been a times. Let's try it again. 0.195 times 1,800. That is an integer, so I should be okay. If you ever get a domain error when you do these, it's because that product is not an integer. So just type it in your calculator in the main page and round to the nearest whole number. So 0.195 times 1,800, sample size 1,800. The other one was, I think it was 15% of 3,000. That is definitely an integer. And I want to do a one-sided. I want to know if this one is bigger than 2. That's kind of why I like writing it. I kind of do it both ways because I'm a little OCD, but I want to know if 05 is whatever. Okay. Test statistic 404, p-value 0.00025. This is overwhelming evidence. That's it. Put those numbers down. Z equals 405. P-value is approximately 0.000. Since this is less than 0.01, we're going to reject the whole. Conclusion, we have convincing evidence that the true population proportion of all teens in 2005 with hearing loss is, alternate, greater than that of 1990.